In this video, we will look at some of the applications of integration to physics. The first problem is a problem about work. To set up this problem, we need a little bit of a story. Once upon a time, there was a fair maiden named Rapunzel, and she was locked in a tall tower of height 27 meters. Now, Rapunzel had long, flowing blonde hair, approximately 27 meters long. Now, Rapunzel was lonely up in her tower, and one day she sees a little kitten wandering by. She decides that she wants a friend, so she ties a basket to her hair, lowers it down, and because kittens are dumb and love baskets, it jumps in. She then hoists the kitten up using her hair into the tower and gains a new friend. The question is, how much work did she have to do to haul the kitten up into the tower? In order to answer this, we need some information. How much did the kitten and the basket weigh? Let's assume for the purposes of this problem that the kitten and the basket together had a combined mass of 1.5 kilograms. We still need to know how much her hair weighs. According to the paper Biomonitoring of Mercury Exposure with Single Human Hair Strand, the average human hair has a mass of 5.4386 milligrams per meter. According to figures online, the average blonde woman has about 150,000 hairs on her head. Putting these two pieces of information together, we estimate that Rapunzel's hair probably weighs about 0.8 kilograms per meter. With all this information in mind, we can get started. We can tackle the problem of moving the kitten and the basket and hauling up the hair separately. Let's talk about the kitten and the basket, as it's the easier part. Together, the kitten and the basket had a combined mass of 1.5 kilograms. Now, force is equal to mass times acceleration. Here, the acceleration is 9.8, acceleration due to gravity. So, the force is 9.8 times 1.5. And to get work, you take force times distance. Therefore, the work is 1.5 times 9.8 times 27, which works out to be 396.9 joules. Now let's tackle calculating the work of hauling the hair back up into the tower. To do this, let's think of the top of the tower as x equals 0, and x increases as you head down the tower. Now subdivide the hair into a bunch of intervals of length delta x, and let xi be any point in the ith interval. Then, the work done to take the ith interval up to the top of the tower is going to be the force acting on that piece of hair times the distance it has to travel. Now, the mass of this bit of the hair will be 0.8 times delta x. The acceleration of this piece of hair will be 9.8 meters per second squared, which is acceleration due to gravity. And so the force acting on this interval of hair is 0.8 times delta x times 9.8. To get the work, we take force times distance. This interval of hair has to travel approximately xi meters to the top of the tower. And so the work done on this bit of hair is approximately force times distance, which is 0.8 delta x times 9.8 times xi. Now, we add up all of these across the intervals, and then take a limit as the number of intervals goes to infinity. What we get is an integral. This integral is the integral from 0 to 27 of 7.84x, which, if you work through, is 2,857.68 joules. Combining this with the amount of work it required to move the kitten and the basket, we get a total energy expenditure of 3,254.58 joules. To put this in perspective, according to the Wikipedia page on joules, 1 joule in everyday life represents approximately the energy required to lift a medium-sized tomato 1 meter vertically from the surface of the Earth. The next topic we'd like to address in this video is that of hydrostatic pressure. Now, if you've ever been in a deep pool or in the ocean, you know that the further down you go, the more pressure you feel on you. This is because there's more water above weighing down on you. We can compute the amount of pressure that you feel as rho times g times d, where rho is the density of the fluid that you're submerged in, g is acceleration due to gravity, and d is the depth. For water, rho is about 1,000 kilograms per cubic meter. And acceleration due to gravity, at least on Earth, is about 9.8 meters per second squared. Hydrostatic pressure is the pressure a vertical plate would feel if submerged in water. Hydrostatic force is the force exerted by the water on this vertical plate. Let's work an example of computing the hydrostatic force exerted on a dam. In this problem, the dam has the shape of a trapezoid. The height is 20 meters, the width is 50 meters at the top, and the width is 30 meters at the bottom. Find the force on the dam due to hydrostatic pressure if the water level is 4 meters from the top of the dam. We choose the vertical x-axis with the origin at the surface of the water. The depth of the water is 16 meters, so we divide the interval 0 to 16 into small intervals of equal length that we will call delta x. In each of these intervals, we will specify a point. The point in the ith interval we will call xi star. What we seek to do is compute the hydrostatic pressure and the area of the ith strip. The ith horizontal strip is approximately a rectangle with height delta x and width what we will call wi. We now seek to find wi. As you can see from the figure, it suffices to find the value of a. Then wi will be 30 plus 2a. We can use similar triangles to say that a over 16 minus xi star is equal to 10 over 20. And then solving this, we get that a is equal to 16 minus xi star divided by 2. Therefore, w is equal to 30 plus 2a, which is 30 plus 16 minus xi star, or 46 minus xi star. Therefore, the area of the ith strip is approximately wi times delta x, which is 46 minus xi star times delta x. Now, if we make delta x small enough, the pressure exerted on the ith strip is nearly constant throughout the strip. So we can see that the pressure on the ith strip is approximately 1,000, which is the density of water, times acceleration due to gravity, times xi star, which is the depth. The hydrostatic force on the ith piece is equal to the hydrostatic pressure on the ith piece times its area. We have computed these two quantities, and so we see that the hydrostatic force is approximately equal to 1,000 times 9.8 times xi star times 46 minus xi star times delta x. And if we add all of these up across all of the intervals, and then take a limit as the number of intervals goes to infinity, we see that what we have is an integral. Precisely the integral 0 to 16, 1,000 times 9.8 x times 46 minus x. Computing this integral yields 4.43 times 10 to the 7th newtons.